All right, so now we're going to talk about circular motion. We're going to see a lot of the same ideas. We're going to see a variation of kinematic equations. We're going to talk about forces again, but we are going to have different variables, and these variables are going to be specific for circular motion. So the first thing we kind of need to define is the rotation of a rigid body, right? So a rigid object is going to be an object where if we have, like a CD, we have 2 points on this CD. If we were to rotate the object, the distance between those 2 points is going to remain the same. So a CD, anything that is like solid is going to be a great example of this. Things that are like liquidy and gooey are not rigid bodies. So for circular motion, we focus on angles instead of distances, right? So instead of displacement, we are going to have angular displacement, or our change in theta. So if we have angular displacement, we can represent this as arc length over radius, right? So our arc length is going to be this value here on the outside of the circle, and our radius is just going to be from the center of the circle to the edge where our point would be. So our change in theta is going to be arc length divided by radius, and this is going to have units of radians, right? So whenever we're doing SOHCAHTOA, right, for our right triangles, we use degrees, but whenever we're talking about rotational or circular motion, we use units of radians, not degrees. So everything is in radians. So if we have a change in theta, or an angular displacement over some change in time, then we have our angular velocity. And this is the Greek letter omega. It is not a lowercase w. And omega, or our angular velocity, has units of radians per second. Why? Because our angular displacement is in radians, and time is, of course, in seconds. So just like we had displacement, velocity, acceleration, we have angular displacement, angular velocity, and now angular acceleration. And this is the Greek letter alpha. It represents our angular acceleration, and this is just our change in angular velocity over a change in time, and it has units of radians per second squared. So the relationship between these is still the same, but now instead of displacement, we have angular displacement. So the most convenient angle measure is the radian, right? So we're not using degrees, we're using radians, right? So we can define theta as our arc length divided by our radius. So if we go around this entire circle one time, then our arc length is 2 pi times the radius. This means that if we go around the circle one time and we replace this arc length with 2 pi r, theta is 2 pi, right? A circle, right? So this makes sense. So 2 pi radians is 360 degrees. So there is a relationship between linear velocity and angular velocity, or if we're thinking about the magnitudes, linear speed and angular speed. So our definition for linear velocity was this change in position, or this linear displacement divided by a change in time. And if I'm thinking about the rotation of this rigid object, yes, I have a change in theta, I have this arc length value, but I also have an initial position and I have a final position here. So my change in linear displacement, my change in position, is going to be r final minus r initial. And this change in position can also be described by the arc length of this object's motion, right? These are two different descriptions of the same motion. And so I can use this relationship to find a commonality, a way to convert between linear and angular motion. So From the previous slide, we know that our change in theta, our angular displacement, is going to be arc length divided by the radius of this circle. So I can rearrange this to state that arc length is equal to my change in theta, my angular displacement, times the radius. Now I can use this relationship to create a definition for my linear displacement has to be equal to my change in theta times the radius of this circle. And I can plug that in to my velocity equation, and I find that linear velocity is equal to a change in theta, right, my angular displacement, divided by a change in time times the radius of that circle. Now, this change in theta over a change in time is the same thing as omega, my angular velocity. So this tells me that my linear velocity is equal to omega, my angular velocity, times the radius of this circle. So I can use this relationship to convert between angular and linear motion. So when we're talking about rotational motion, generally we consider the linear velocity to be tangential velocity. And this is because it is tangent to the circle, right? So we see here on the bottom the tangential velocities or the linear velocities of these objects. And the linear velocity is proportional to the distance from the center of rotation, right? That's because our linear velocity is equal to the radius times omega, right? This omega is scaling, so it is proportional to the radius, meaning that if I change the radius, it changes my linear velocity. But every point on a solid object has the same angular velocity. Why? Well, that's because our definition of angular velocity is a change in theta over a change in time. If my theta, here we have 2 points on a circle, right? These thetas are the same value, right? So every point on a solid object has to have the same angular velocity or the same speed of rotation. So when the speed of a point moving in a circle is constant, we call that uniform circular motion. And the time for the point to travel completely around the circle is called the period of the motion. So one complete revolution around this circle is going to be the period. The frequency is the number of revolutions per unit of time. So we can define the frequency as 1 over the period. And this has units of hertz. So the speed, right, or the magnitude of my velocity is the total distance traveled by divided by the total time taken, right? So speed is going to be total distance divided by total time. So if total time is going to be the period and the total distance is going to be one whole revolution around the circle, it's going to be 2 pi, then we can take v is equal to our change in theta over our change in time times the radius. We get that v is equal to 2 pi times this radius over the period. Because frequency is 1 over the period, then the speed is going to be 2 pi times this radius times the frequency. So then for uniform circular motion, our angular velocity is the same thing as 2 pi times the frequency. And we'll come back to this whenever we get to waves and sound. And I think it's important to note that what we're showing here is not really new physics. What we're showing here are just mathematical relationships between different variables, different terms that we use in physics. So these are all just mathematical relationships. So when an object is rolling, like rolling across a surface, it is not only rotating, but it is also translating. And I think that this little image is a great example of that, right? Whenever we have an object rotating, it is in one spot. When we have an object translating, it is moving from one position to another position. So for rolling, we have both translation and rotation. And so the relationship between the angular speed of this wheel and the linear speed of that axle can be found through these relationships that we have been deriving. So what is the relationship? Well, it's just that the linear velocity is equal to the radius times the angular velocity. So just like we had kinematic equations for translational or linear motion, we also have kinematic equations for rotational motion, right? So in translational, we had our change in position. In rotational, we have our change in theta, and we have this relationship between the two. In translational, we had linear velocity. In rotational, we have angular velocity. And we have this relationship that allows us to convert between linear and rotational velocities. But what about acceleration? Well, thankfully, it follows the same pattern. The relationship between linear acceleration and angular acceleration is just proportional to the radius of the object. Then we're going to have a new type of acceleration to talk about, and this is going to be centripetal acceleration. And there will be a relationship between centripetal acceleration and the linear velocity of this object. So we also have the kinematics, right? We had our initial kinematic equation where final position is equal to initial position plus the average velocity times time. It has the same form in rotational motion, right? Now we just have our final theta is equal to our initial theta plus the average angular velocity times time. And this is true for all the rest of the kinematic equations, right? They have a rotational counterpart. And it's important to remember that in all of these, our linear acceleration had to be constant for translational or linear kinematics, and so our angular acceleration has to be constant for rotational kinematics. So what about that centripetal force? Well, I want to real quickly go through some definitions and relevant terminology because I personally think that it's helpful, right? So we're talking about linear or translational, and I mentioned this tangential velocity. So what does tangential mean, right? It's just a straight line that touches a curve but does not cross that path at any point. So centripetal just means towards the center of a circle. I like to think about this like centripetal has the word petal, and petals attached to the center of a flower, so centripetal acceleration points towards that attachment of a flower petal. And then oftentimes we hear about centrifugal forces, right? So this is actually a fictitious force. It has to do with Newton's first law, this law of inertia. But fugar means to flee, so it's fleeing away from the center. These centrifugal forces point away from the center of the circle or outwards. So what is centripetal acceleration, right? So for a particle that is undergoing uniform circular motion, the direction of that velocity is continually changing, right? So if I have an object, imagine that's a closed circle, and it's moving around a circle, right? That linear velocity is continually changing. It may not be changing in magnitude, but it is absolutely changing in directionality. And so if it's changing in directionality, it has to have some sort of acceleration. And we call that acceleration the centripetal acceleration, right? So our acceleration, centripetal acceleration, is going to be equal to this tangential velocity squared divided by r, where r is the radius of this circle. And it's going to be pointing inwards at every point along the path. So there is a relationship between tangential and centripetal acceleration, right? The tangential acceleration, or the acceleration that's tangent to the curved path, is going to affect the magnitude. The centripetal acceleration is going to affect the directionality of this velocity. So the centripetal force is the force that comes from centripetal acceleration, right? So a force acting towards the center of the circle is going to be negative, and a force acting away from the center of the circle, is going to be positive. So our centripetal force is going to be negative. So we have the force centripetal is equal to the mass times the centripetal acceleration, and my centripetal acceleration is going to be v squared divided by r. So my centripetal force is going to be negative. That represents the directionality. It's acting towards the center of the circle, times the mass of the object. It's tangential velocity squared divided by r, where r is the radius of where we are from the center of the circle. So what's interesting is that this centripetal force is actually another name for a force that we have already talked about, right? So here's 3 examples of objects that would have a centripetal force, right? Some sort of centripetal acceleration. And the centripetal force is technically another force that we've already talked about, right? So if we think about a satellite or the Earth orbiting the sun, we have a centripetal force that's pointing towards the center of the circle. So what is another thing that we could call this force? Well, this is just the gravitational force, right? So the gravitational force is the force that's causing this centripetal acceleration in that problem. So what about like a laundry dryer? There is a centripetal force, right? Your clothing is feeling a centripetal force. What is the force that is causing this centripetal motion? Well, this is going to be the normal force, right? Your clothing is touching the surface of the dryer basket wheel thing, and it is causing this normal force. This normal force is our centripetal force. What about an object that is like a car that's going around a track? Well, in this situation, that centripetal force is the frictional force between the tires and the asphalt.